Hi there, welcome back. In the previous video, we looked at current. We saw how current is conserved in a circuit, how it splits and merges at junctions. And now we're ready to talk about electric potential at different parts in a circuit. And in doing so, we'll address another law called Kirchhoff's loop law. The specific questions we'll answer are things like, what happens to potential difference at different points in a circuit? How does potential change across a resistance and across a battery, for example? And then we'll look at an entire loop and see what the potential difference across an entire loop in a circuit is. Let's take the example of a simple circuit that's shown here. It's got one battery here at the top and one bulb at the bottom. First, since this is the first time we're seeing circuit notations of things like batteries and bulbs, let's take a minute to discuss that. So far, we have shown batteries like this, with a rectangle and a stub at one end, and the stub end was the positive end of the battery, which was the higher potential, and the opposite end was the negative end, and the wire was connected to the two ends of the battery in the circuit like that. We could have also shown it vertically, where the battery could be standing up like this, with the stub at one end, which would be the positive end, other end is negative, and the wires could be going like that. Well, the circuit representation of batteries corresponding to these examples will look like this. We show a battery with one long line and one short line right next to each other, and then the wires go like this. The long line represents the positive end of the battery, and the other one represents the negative end of the battery. So these two are equivalent. And similarly, if I wanted to show this over here, I would show a long end at the top to represent the positive and a short end at the bottom to represent the negative. And the wires would go like that. Now, as a word of caution, I've seen students a lot of times representing batteries like this. Please don't do that. This would not be a battery. This would be a parallel plate capacitor. When you draw a battery, make sure that one end is clearly longer than the other, which would represent the positive and negative ends and tell you that what you're looking at is a battery. Secondly, it is okay, and your textbook does this often, to show multiple representations in one shot. So you could show something like this. This whole thing is still just one battery. And it really doesn't matter for our purposes whether we show it once or show it 2 or 3 times. We would typically identify the EMF or the potential difference across the battery as a number right next to it. So the number of times we show these symbols does not matter. The other thing, as a matter of convention, is that typically in circuits we show the positive end to the left and negative end to the right if the battery is represented like this, or if the battery is standing vertically, it's customary to show the positive end at the top and negative end at the bottom. Not that you couldn't show it the other way, but this is just a generally accepted practice. Next, the typical representation for a bulb in a circuit is that the wire goes through like something that looks like a filament, and we put a globe around it, and that represents a bulb. And here we had representations of batteries. Okay, I've cleared up those notational examples that we used, and coming back to our example here, let's say that this is a 12-volt battery, so I'd write that over there, and let's say this bulb has a resistance of 6 ohms, so I'll write that over here. Now, as we discussed, the long line is the positive end of the battery and the other end is the negative end, and we know that the current in a circuit goes from positive to negative, so the current is going to come out of this positive end and go in this direction in this circuit, through the bulb over here, out of the bulb, and back to the negative end of the battery like that. So these arrows show the direction of current. And given that we have just discussed Kirchhoff's junction law in the previous example and conservation of current, we now know that because there is no junction here at all in this circuit, whatever is the current that comes out of the battery, if we call it I, it's got to be the same current that enters the bulb, and the same current that leaves the bulb, and the same current that goes to the negative end of the battery. So the current in this entire circuit will be the same everywhere, because there is no junction and current has to be conserved in a circuit. Okay, but our goal in this video is to look at the potential difference at different points in the circuit. So let me redraw the circuit over here and label certain points so that we can see what the potential difference is as we go across the circuit. So I'm going to label the point right outside the positive end of the battery as A, the point just before the bulb as B. By the way, sometimes I don't draw this globe around the bulb, but let me go ahead and do that over there. But if I miss it, you'll know that it still is a bulb. C is my point in the circuit right after the bulb, and D, let's say, is the point in the circuit just before the negative end of the battery. And just for completion, I have just shown the direction of current in the circuit over here. Before we get to potential difference, one quick note on the direction of current. As we discussed, it goes from the positive end of the battery to the negative end of the battery in the circuit. Now, if you zoom in and look inside the battery, I'm going to zoom the AD points over here and draw the battery here. Here's my D point, here's my A point. And if I want to look at the direction of current in this circuit, it's going to the left at A, going to the left at D. So inside the battery, the current is going like that. So it's going from the lower potential or the negative end to the higher potential or the positive end inside the battery. And that's important to note. We do say that current in a circuit goes from high potential to low potential. And that's true. But inside the battery, it is opposite. It goes from low potential to high potential, as we see here. So back to potential difference. Our goal is to figure out what happens to the potential across these points. So I'm going to show you some notations. If I write delta V, you know that's the change in potential. And if I further write delta V subscript AB, you'll know that it's the potential difference between points A and B in the circuit. And that's defined as the potential at point B minus the potential at point A. Remember, change is always final minus initial, like in physics 1, so we continue that same notation over here. So what would that be in this case? Well, all I have is an ideal wire here. And as we discussed before, the potential drop across an ideal wire is 0. So potential at B and potential at A will be identical. So the potential drop from A to B is simply 0. Then we have a potential drop between B and C. So this would be VC minus VB. And we know that when we go across a resistor, the potential in a circuit drops. So let me collect that fact over here. Across a resistor, potential drops in the direction of current. So since my current is going from B to C, C is at a lower potential than B is. So in this case, this would be a negative number. I'll come in a few minutes to what that number is. Then I got potential from C to D, which would be the potential at D minus the potential at C. Once again, I only have ideal wire over here, so there is no potential change. So that is also 0. And finally, I've got in the direction of current VDA, which is VA minus VD. And now because I'm going across a battery in the direction of current, I'm going from a lower to a higher potential as we discussed. So this would be a positive number. So let's write that down over here. Across a battery, V increases in the direction of current. Okay, so let's now work with some numbers. We had the potential difference between A and D given to us as 12 volts. That was the EMF of the battery. And since the potential at A and potential at B are identical to each other because of the ideal wire and the 0, and the same thing with D and C are identical to each other because of this 0 and this ideal wire, the difference of potential between A and D would be the same as the difference of potential between B and C. And so this would also be 12 volts, where B is a higher level of potential than C is, just like A is a higher level of potential than D is. All right, with all that in mind, let's now look at what happens to the potential difference across an entire loop in a circuit. Starting here, the potential across the battery was a plus 12 volts. So this delta V dA was plus 12 volts. And as we saw before, delta VAB is simply 0. Delta VBC, there's a drop in potential of 12 volts. So this would be minus 12 volts. And then delta VCD is 0 in this case. So clearing some room and going back over here, my delta V loop, which is the potential difference across the entire loop. And for example, let me just start at A and work my way across the entire loop. So that potential change would be simply the potential change between AB plus the potential drop between BC. Sorry, there's a delta over here, plus the potential change across CD, plus finally the potential change across DA. That completes the entire loop. And we know all these values, so let's see what that ends up being. VAB is simply 0. VBC was a negative 12 volts. Across the resistor, there was a drop. VCD was 0, and VDA was a positive 12 volts. And when I add all of this, I simply get 0 volts. And that's what Kirchhoff's loop law tells us. It basically says that in any circuit, if I go through an entire loop ending at the same point at which I started, the sum total of all the potential changes I encounter have to equal 0. Now, all that might have seemed quite obvious in our simple example, but it also holds good in a more complex circuit, as I have shown over here. By the way, these squiggly lines are the symbols for resistances in circuits. This circuit has multiple loops. I've got one loop over here. I've got a second loop that is a larger loop that goes through this single resistance in the battery. And I have a third loop that doesn't even involve a battery, that just got resistances over here. Kirchhoff's loop law works for all of these loops. So if I take the first one, the green loop, and if this is my starting point, by the time I make one full loop across that circuit, the sum of all the potential changes must add up to 0, and they will. Same thing with the red circuit. If I start over here and go across this one single resistance and across this battery, the sum of all the potential changes I encountered must also equal 0. And in the third loop, if I started at any point, let's say over here, and worked my way across this resistance, the second resistance, and this third resistance, in the direction of my movement through the loop, the sum of all the potential changes will add up to 0 by the time I come over there. And if you think about it in the gravitational sense, when you run a race, you might go up a hill and down a hill, but as long as you start and end at the same point, the total elevation gain and the loss that you have has to equal 0 because you are ending up at the same point. Same thing in the electrical circuits. To summarize, in this slice of physics, we learned Kirchhoff's loop law. First, we saw that in the direction of current in a circuit, potential drops when you cross a resistor and potential increases when you cross batteries. Then we looked at Kirchhoff's loop law, which told us that the total potential change around a full loop in a circuit is 0, and we saw a couple of examples of that. And finally, in doing all this, we saw that while current goes from higher to lower potential in a circuit outside the battery, the story inside the battery is reversed, where the current goes from low to high potential inside a battery. That's what the chemical energy in the battery does in moving charges up the hill. Thanks. I'll see you soon.